Permanent Reservoir Monitoring, or PRM, holds the promise of improved reservoir management to increase production and total recovery from existing and new oil and gas fields. Stingray has developed Fosar, a fibre optic-based solution delivering reliable and high-fidelity seismic information, enabling cost-effective PRM with the capacity to increase total recovery by 5 to 10% or maybe more. To achieve this, an array of seismic sensors is installed on the seabed and linked to a recording system at the surface. Once installed, detailed reservoir characterization is possible. Furthermore, changes in these reservoir characteristics can be tracked over time, even on demand, to understand changes in a reservoir's production performance. All of Fosar's subsea components are passive fibre optics, powered by light. This means the system is inherently reliable and is capable of supporting very large numbers of sensor channels with lightweight, small diameter cables requiring only a small number of connections. Power requirements are low and is restricted to the surface electronics and recording equipment mounted on the platform. Stingray's Fosar solution makes PRM technically feasible and economically viable. Stingray's Fosar solution enables cost-effective and highly repeatable time-lapse or 4D seismic. The time-lapse analysis improves our understanding of reservoir behaviour over time, as well as reducing the drilling risk for future production and injection wells. Time-lapse or 4D seismic using marine towed streamers is a well-established technique for reservoir management, yet has known limitations. It produces single-component data. 2 vessels operations are required for wide azimuth surveys. There's usually restricted reservoir illumination around the infrastructure, and data is less repeatable due to positioning errors and noise. Stingray's permanently installed Fosar solution overcomes all of these limitations. The Fosar array is permanently installed on the seabed to deliver repeatable, high-fidelity 4-component data. Permanent installation ensures constant receiver positioning, improved coupling and low noise for higher quality and more repeatable data. Installed seabed receivers also facilitate wide and multi-azimuth recording for improved illumination and multi-component analysis. Stingray's Fosar array is laid in sections on the seabed. Each section, typically several kilometres long, is connected to a hub or backbone. Optical fibre from the hub or backbone is then brought to the surface to join the Fosar interrogation system, mounted in this illustration on a platform. Stingray's Fosar system has been designed as a cost-effective and reliable PRM solution, capable of supporting the tens of thousands of sensor channels needed to image reservoirs. Stingray's Fosar solution is a key tool in transforming reservoir performance, with the capacity to increase total recovery by 5 to 10% or higher through information-driven decision-making. Multi-component installed Fosar systems are used to improve reservoir models as well as monitor production. The data is used to characterize reservoirs and improve structural and stratigraphic understanding of the subsurface. Repeat or time-lapse datasets are used to update and maintain both static and dynamic reservoir models, assisting in the optimization of future production. Stingray's Fosar can be deployed in all reservoir situations requiring field monitoring. The fibre optic architecture enables a large sensor count for extensive coverage of large areas at densities required by reservoir and economic considerations. Using fibre optics also provides the capacity to tap into installations with long tiebacks, tens or even hundreds of kilometres away. Fosar Deep is designed for subsea installation in deep water fields with complex infrastructure of tethers and risers. Results are what matters in the responsible management of today's reservoirs. The application of technology is increasing production and improving both costs and margins. Stingray's Fosar PRM solution is reliable and cost-effective. Stingray's subsea engineering expertise and partnership with installation specialists ensures that Fosar deployment and burial causes minimal interference with ongoing operations and existing infrastructure. There should be no downtime, no shutdown or lost productivity during installation. Stingray's Fosar array has a 20-year design life. This is achieved through the use of proven and passive fibre optic components, a low component count and consistent manufacturing processes. There are no electrical or moving parts in the water. These are usually the components with the lowest mean time between failures. The high sensor capacity per fibre enables the use of a small diameter riser to the topside recording system. Stingray's Fosar uses existing and proven subsea connectors. The riser terminates at the interrogator and recording system that's installed in the local equipment room. The interrogator and recorder are compact units with low power requirements, mounted in 3 standard 19-inch racks. Stingray brings together both geophysical and subsea operational experience, combining this with a comprehensive approach to planning and the light and flexible design of the Fosar system, which enables safe and efficient installations in and around existing infrastructure. Stingray's Fosar is a passive fibre optic system with a very high seismic sensor count. The system is installed on the seabed for permanent reservoir monitoring, PRM. To achieve this, the Fosar system employs an optical architecture that combines both time domain multiplexing, TDM, and dense wavelength division multiplexing, DWDM. The sensors are physically separated along the length of the optical fibre, and this means that pulses of light returning from each sensor are separated in time. This is the time division multiplexing. A further level of multiplexing is required, and to achieve this, we use light sources with a number of different wavelengths, or wavelength multiplexing. As the light pulses travel down the backbone fibre and into the array, a switching device called a wavelength drop multiplexer separates the pulses of light at different wavelengths and directs each wavelength to a different set of sensors. The pulses of light at different wavelengths returning from each set of sensors are then combined again and sent back up the backbone cable to the interrogator on the platform. The fibre optic sensors are what allow us to listen with light. The passive fibre optic sensors are designed so that an incident pressure or shear wave induces a strain in an optical fibre, causing the length of the optical fibre to change. Although these changes of length are on the scale of the diameter of an atom, they can be measured very accurately by measuring the change in phase of light being reflected back from the system. The Fosar architecture maximizes the number of channels which can be interrogated on a single fibre pair, which in turn minimizes the number of fibres required in each length of sensing cable. The architecture makes cable lengths of 5 to 10 kilometers possible with a handful of fibres. It also reduces sensor-to-sensor crosstalk and lowers complexity and component count of the optical sensor unit and the surface-mounted optoelectronics. Stingray's Fosar system has been designed as a cost-effective and reliable permanent reservoir monitoring system, capable of supporting the tens of thousands of sensor channels required for accurate imaging of reservoirs over time. Listen with light using Stingray's Fosar system to enable cost-effective permanent reservoir monitoring.